So at this time, let's make a list of the questions that students have about chapter 6. So what concepts of chapter 6 do we need to review? Balancing equations is chapter 7. We're working on chapter 6 now. So on chapter 6, excellent, we have Lewis structures. Polarity. What other concepts from chapter 6? Attractive forces. So in terms of making ionic compounds, like how do we go from name to chemical formula? That is called nomenclature. Other concepts from chapter 6. So right now we are making a list of the concepts of chapter 6 that students want to review. So as people are coming in, just put in the chat or unmute yourself what concepts of chapter 6 you would like to review. Because remember that in this review, we cannot cover 2 weeks of material, which is pretty much what we have in the exam. So I cannot re-lecture 2 weeks of material. So this is a little bit more targeted. Excellent. So if this covers the questions that you guys have, let's actually go in order. The first thing that we are going to tackle is going to be nomenclature. Okay. Now, when it comes to nomenclature, let me just, I will answer your question about bond polarity or molecular polarity when we talk about polarity. So let's tackle first nomenclature, as I was mentioning. So one of the main keys when it comes to nomenclature is going to be, let me actually put some lines in this paper, because if not, my writing is going to get a little bit disordered. Give me one moment, because it froze on my side. Okay, now it's working. So when it comes to nomenclature, especially if we are going from name to chemical formula, there's a few things that you guys have to watch out, okay? The first thing is that you guys must know, okay, if you have an ionic compound or a covalent compound, that is a must, okay? Because if you have an ionic compound versus a covalent compound, then you know that overall there's a way in which we actually show you, okay, how to write the elements that are, or polyatomic ions that pertain to that name, okay? So a few things that you need to deal with when it comes to ionic compounds. The metal always comes first, okay? The metal always comes first. Now, when it comes to metals, okay, remember that you need to know what are going to be the charges, especially if they live in 1A, 2A, or 3A, okay? So if you live in 1A, your charge is going to be +1. If you live in 2A, it's going to be +2. If you live in 3A, if you are aluminum, gallium, and indium, you're +3. Only those three, okay? Now, if your metal is in group B, there are 3, okay, transition metals that only have 1 charge. That is zinc, cadmium, and silver. Let's put it in the chat. What is the charge for zinc and cadmium? They have the same one. Excellent, +2. What about silver? What is the charge of silver? It's not 3. Excellent, it's +1, okay? So that's in group B, right? Now, for the rest of group B, Lisbeth, do you mean for silver? The question is how to know if it's for 1. I don't understand. Are you talking about silver? You can unmute yourself. Oh. So now, how do you know the charges of the rest of group B? The Roman numeral is what gives you what is the charge, okay? And that's pretty much it when it comes to the metal. Now, let me just move this a little bit to the side. What about if we're dealing with non-metals or polyatomic ions? Okay. And remember that the reason why the metals, we have this deal going on is because they form the cation. On the anion portion of your ionic compound, it could be a nonmetal, or we have polyatomic anions. Where do you get those? Okay, let me show you. If you're going from name to chemical formula, when you go to the slides for chapter 6, for your polyatomic ions, you need these tables in slide 7. So slide 7 is where you get the information for the polyatomic ions. When it comes to the nonmetals, now we're talking about slide 10, specifically right here. That's where you get your nonmetal information. If I'm not mistaken, this is table 6.1. It's just that table 6.1 is a little bit larger. It actually has some names for cations, which is the name of the elements, okay? So let me just verify that it is table 6.1. Let me tell you where you can find it in the textbook. It's on page 168, okay? In the slides is on slide 10. So going back to the notes. For the anions, you actually get the names, the chemical formulas for the anions. This is table 6.1 in the textbook on page 168, or slide 10 in the presentation. And then the polyatomic anions is going to be slide 7. There's a table that comes from the textbook, and there's a table that is actually part of the reference list for exams, okay? So at least those are the two components in terms of ionic compounds. Any questions about ionic compounds? We're gonna practice now, and then we're going to move on to the covalent. Any questions on, okay, these are the parts of my ionic compound. So when it comes to strategy, when you guys encounter the questions of going from name to chemical formula, you need to have all this information handy to you. That's your strategy. If you don't have this, then you will be searching for it, and it's gonna take time. So it's better to know that when you're going from name to chemical formula, you need this information. Let's actually do some practice. Let me see what Maria has here. Awesome. So this file that I am showing you guys here, let me see if I can copy this. This is actual work. I had a tutor for this class long time ago, and she made this worksheet, but then I can only use them in reviews. I cannot just give them to all of the classes because it's not my material. It's actually material from another person. So, let's see. Oh, it took the whole thing. But let me see, maybe I can block these. Or actually, I can crop it. I should crop it. That'll be easier. And what I will do, you guys, is that I will post this notes in Canvas, so you guys will be able to have it, okay? So these are some examples for ionic compounds. We're going from name to chemical formula. Okay, these are all ionic compounds. Except this one. That one is not ionic. That one is a covalent compound that we name it like ionic, but I didn't teach you that. So let's get started going through these. First name that we have aluminum. Let's put it in the chat. What is the symbol for aluminum? Aluminum lives in 3A. So what is the charge for aluminum? If you do +3 or 3+, it's going to be the same thing, okay? Sulfide refers to what element? Sulfide. Sulfur. If you look at the table on slide 10 or table 6.1 in the textbook, since sulfur is in group 6A, it has a charge of -2. Okay, now the rules say that we're going to take the number and make it the subscript of the neighbor. The number, make it the subscript of the neighbor. So the final answer is going to be Al2S3. Because when we have an ionic compound, okay, understand that those charges are going to cancel each other. If we look at the math, Al is +3 always. S is -2, but we have 3 of them. When we multiply these, look, +6 plus -6 equals 0. So that's why we don't deal with the math that I just illustrated. We just exchange the value of the charges and make it the subscript of the neighbor. That's it. So you don't have to, deal with the math. You guys have enough math to do for this exam, okay? So in a similar fashion, what is the chemical formula for magnesium phosphide? Magnesium phosphide is made out of Mg. It lives in 2A, so it's +2. Phosphide refers to phosphorus. Excellent. This is Mg3P2. Let's do the next one. Calcium oxide. Ca2 plus, O2 minus. Again, calcium lives in group 2A. That's why it's 2 positive. Oxide lives in 6A. That's why it's -2. Great job, you guys. This is CaO. Potassium sulfide. Potassium, symbol is K. Charge is +1. Sulfide is S. And it has a -2 charge. Excellent, K2S. We have iron 3 oxide. Again, the Roman numeral tells me what's going to be the charge of my iron. Fe +3. Oxide is O2 negative. What is the chemical formula? Great. Fe2, sorry, Fe2O3. Okay. I'm going to give you guys a minute to do the last three: chromium 2 fluoride, lead 2 oxide, iron 3 chloride. What is the answer for letter N? Great job. CrF2. What about for letter P? Awesome. What about letter R? You guys got this. Don't feel nervous about the exam. Okay, so this is at least, you guys saw type 1 metals, you saw type 2 metals, and then you saw non-metals. Let's do practice problems now with the polyatomics. I need to. Let's get started with the polyatomics. I will do, let me just erase some of the ones that I see here that do not pertain to the class, like this one. Let me see what else is here. No, everybody else is good. Awesome. So here we have potassium nitrite. Remember that when it comes to the polyatomics, the resources that you need is going to be slide 7. That's where you have your 2 tables of polyatomics, okay? You will still incorporate the information that we talked about a few moments ago. So potassium lives in group 1A, is +1. From the table, nitrite, that's NO2 -1. Okay, so when we combine these, is going to be KNO2. A hint that, because in the exam, it's not going to direct you to like, this has a polyatomic ion. No, you need to know that there is a polyatomic ion. How do you know that you have to look at the table of polyatomic ion? When the ending for most polyatomic ions end in ITE or ATE, ite or ate. You know that you're dealing with a polyatomic, and it's going to be in the second word. There's a few polyatomics that do not end in ITE, ite, or ATE, ate. Okay, how do you know? That is just memorization. For example, there's only 3 polyatomics. Well, 4 if you count ammonium. But out of the negatively charged polyatomic ions, hydroxide, which is in H, peroxide, and cyanide. Those are the only 3 polyatomics that do not end in ite or ate. Regina, I don't understand your question. Suffix. Whenever we're dealing with polyatomic ions, we just use and it's from name to chemical formula. The polyatomics, there's only one that has a prefix, and that is dichromate, because that is the name of it.
No, you were asking how do you know about polyatomics? So I was like, well, typically you just look at the suffix of the end of the word. Like potassium,
exactly.
Potassium is in the periodic table, but nitrite's not.
Exactly. And like I was saying, that's a good point. That suffix, which is the proper way to mention, is the ITE, ATE, but you have to memorize there's 4 polyatomics, at least 3 that are negative and 1 that is positive, that do not end in ite or ate. Ammonium, which is positively charged, and then you have hydroxide, peroxide, and cyanide. So this is information that you basically, in a way, have to memorize. There is part of the concepts in this class that you have to memorize. Okay, so in the next one, we have ammonium. And please do not confuse ammonium with ammonia. They're cousins. Ammonium actually comes from ammonia, but don't confuse the chemical formulas. Ammonium is a polyatomic ion, and its chemical formula is NH4+. Hydroxide, by looking at my table, is OH-. Okay, whenever you have charges that are just opposite from each other and is the same value, basically we are not going to cross the values. They're just going to cancel each other. So for this one, we have NH4OH as our chemical formula. Okay, I'm going to do letter L with you guys, and then we're going to proceed to practice the rest. When it comes to magnesium, this is Mg plus 2, nitrate, NO3 -1, okay? As you can see, the charges are not canceling each other. So in this case, we have to move this value as the subscript, move this value as a subscript, okay? So magnesium is going to get a subscript of 1, but subscript of 1 is never written, okay? Then NO3 is a whole unit. It's going to get a subscript of 2. And instead of this thing looking like a 32, we need to wrap it in a blanket. Whenever your polyatomic ion has a subscript of 2 or more, put it in parentheses. Don't be extra with the parentheses. Don't be putting parentheses everywhere, because you will not get the correct answer. The parentheses are only utilized on polyatomic ions, okay, or the Roman numeral when we're writing names. And it is when your subscript is 2 or more, okay? Let's do letter N. We have aluminum sulfate. So this is Al plus 3, SO4, 2 negative. What is the chemical formula for it? Again, the charges are not canceling each other, so we have to exchange the value of the charges and put it as the subscript of the neighboring atom. So aluminum sulfate. Excellent job. This is Al2. We put this in parentheses, 3. Lead 4 nitrite. That means that we have Pb plus 4, NO2 -1. Be careful with the capitalization of your elements. Remember that is capital capital A, small letter L. If you capitalize both letters, the program is going to tell you you're incorrect. Remember that also with the O's and the zeros, do not put a zero instead of an oxygen. Canvas is going to, recognize it as a zero and not an oxygen. You will not get the credit. Okay. So please be mindful of that. It might not be a big consequence if you were handing in like a paper, because it's going to be, read by your instructor. But for us in the sciences, that difference between, oh, it looks like an capital O, I'm just going to put a zero, it's the same thing. No, remember that Canvas is just programmed to accept certain formats, and it knows what is a zero versus a capital O. Excellent job. This is PbNO2, 4. Next one, lead 2 sulfide, Pb plus 2 SO3 negative 2. What's the chemical formula of R? Pb SO3, one more. Vanadium plus 5, S2O3, 2 negative. So what is the chemical formula for T? Excellent job. It's going to be V2 and in parentheses S2O3, outside the parentheses 5. When you guys are entering this into the exam, just like I did in the homework, just like you guys did in the chapter quiz and the extra credit quiz for those of you guys that are going to do the extra credit quiz before the exam. When it comes to chemical formulas, the only thing that you cannot format is the subscripts. So you're going to put them as whole numbers. So understand that when you type it in, it's going to look like what you guys are doing in the chat, just because we cannot do subscripts whenever we're filling the blanks, according to Canvas. So whatever you guys are typing in the chat, thank you for putting it in that order, because that's what it looks like. And like somebody pointed out on the chat, yes, you need to put a space between the name and the Roman numeral. The instructions say you put a space in between the cation, the Roman numeral, when you use it, and the anion. You always do that, okay? Especially if you have polyatomic ions that have a name like dichromate. You don't do di space chromate. No, it's one word. Dichromate is one word. Hypochlorite is one word. So be careful with those things. Any questions on going from name to chemical formula for ionic compounds? Then let's move on to when you have names to chemical formula, but for covalent compounds. The main thing there is the prefix, you guys. The common mistake that I see in exams is that people get too happy and they apply the rules of ionic compounds onto the covalent compounds. Meaning, if they have something, let's say, for example, if you have hydrazine, which is in the list that you guys need to know for the common names, right? Hydrazine is N2H4. All of a sudden, I see people that are like, oh, wait, I can do this. And it's going to be NH2. NH2 is not hydrazine. So I never in the teaching have ever told you simplify the subscripts for the covalent compounds. I never told you. So please don't do that, because that is not the rule for covalent compounds. I do not tell you if it's ionic or covalent. That is a skill that you need to bring. I don't tell you if you're dealing with ionic or covalent compounds. You're going to have, a number of names that you're going to type the chemical formula. You're going to have chemical formulas that you're going to type the name. And you don't have to tell me if it's ionic or covalent. Like that for ionic and covalent is going to be similar to what you guys have done before, in which I give you a pair of atoms and then you tell me, is that going to make an ionic compound or a covalent compound? Okay, so again, for covalent compounds, we're going to pay attention to the prefixes. Because we're going to have two nonmetals, and then the prefix are going to tell us how many of each do we have. Let's practice. So there's a question in the chat. How would you know which one is asking for, like ionic or molecule? Wait, you mean like, how do you know if it makes an ionic versus a covalent or molecular compound? Is a problem like this. If you have two nonmetals, okay, you have a covalent compound. If you have a metal and a nonmetal, that's ionic. If you have a metalloid, metalloids and nonmetals make covalent compounds. It's just that here we don't have it. So again, metal, nonmetal is ionic. Non-metal, nonmetal is covalent. Metalloid, nonmetal is also covalent. There are no compounds for metalloids and metals. So that's how we know if something is ionic or covalent. That's something that we did in class.
Professor, you said metalloid and non-metal, right?
Yes. because at least in my years of training as a chemist, I have never experienced, bought, or seen a compound between metals and metalloids. I have never worked or anything like that. Most of the time, whenever we have metalloids, they are paired with nonmetals and they make covalent compounds. So going back to our notes. Here, again, the first word is going to signify what is going to be the first nonmetal. The second word is going to be the "ide" ending, which is in slide 10, that is going to tell you which nonmetal you have. The prefix is going to tell you how many you have, okay? So if I use my highlighter tool, here we have phosphorus. Let's put in the chat, what is the symbol for phosphorus? Great, P. Then sulfide refers to what element? Great job. Sulfur. Now we go to the prefixes. The prefix will tell me how many I have of each. Tetra. How many is tetra? Great. How many is nona? Great. 9. So this is a 4 and this is a 9. Okay. For those of you that are like, where do you get these prefixes? Let me show you. In the slides, the prefixes are on slide 12. It's in table 6.12 in the textbook. That's where you get the prefixes, the words for the prefixes. Let's go back to our examples to just finish up this concept. We have hydrogen monoiodide. Okay, what will be the chemical formula for that? Hydrogen monoiodide. Great. This is HI. This refers, let me just use my highlighter tool. Hydrogen is right here. There's no prefix if you only have one hydrogen. Iodide represents iodine, and mono says that there's one. Where do we find the chemical formula of nitrous oxide? And please don't say Google. So that is a common name. That's a good one. Don't search it on Bing. Great. I gave you guys a list. Oh, Yahoo, that's another choice. Let me tell you, and I just want to warn you, in this exam, students sometimes say like, you know what? I'm not going to listen to the professor. Professor Google is going to help me to do the exam, find all these chemical formulas and find all these names. So I'm not going to struggle, you know, and Google always have the right answer. Please don't try that. Please don't. Google not always has the right answer. You will spend so much time on Google trying to just get whatever answer, and it's not going to help you. It's better that you know the rules and you perform the rules that I give you. So be mindful of that. Even if you're tempted to be like, I'm just going to Google this name. Trust me, I've already Googled it. So I know what's out there. And I know when Google has the right answer, and I know when Google has the wrong answer. So for all my Googlers out there that think that Professor Google is going to help them in the exam, No, that's not the case. It's better to just apply this. So like you guys said, there's a common name. There's a table for common names, and that is also in the study guide. And you can see that nitrous oxide, the chemical formula for it is N2O. Phosphine is also in that list. What is the chemical formula for phosphine? Great, pH3. And I think we have used at least that list often, that that table, there's two ways that you can find that common list table. Well, there's three ways if I'm not mistaken. Slide 13. You can find it in slide 13. Resource number 2 is the study guide. Resource number 3 is the reference list for exams. Those are the three places to find it. Let's move on to the next one. Hydride is something that I didn't give you guys specifically, okay? So I'm going to skip this one because hydride is something that I didn't give you guys this summer. So let me just cross it out. But hydride will be when hydrogen is the next nonmetal. For those of you that may have to take other chemistry classes, let's just finish these up. Nitrogen trifluoride. What would be the chemical formula? Great. NF3. What about carbon disulfide? CS2. Great. So remember, the way that you guys are entering in the chat, that is how you will enter it in the exam, right? We are not formatting that subscript. I'm just formatting here because I'm handwriting it. Letter P, disulfur dichloride. Excellent. S2Cl2. So this is one of the examples that, again, some students are like, oh, but there's a 2 and there's a 2. Let me just divide. No, 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 no. That was never a rule for covalent. That rule applies only to ionic compounds, okay? And lastly, carbon tetrachloride. Great. Questions? Going from name to chemical formula. Okay. The next thing, give me one moment. Excellent. There's a question in the chat for naming SBF4, which was in the chapter 6 homework. That's going to be part of this crew. SBF4, okay? This is the opposite, going from chemical formula to name. So, antimony, along with tin, bismuth, and lead, okay, are going to be elements that even though they are a little bit closer to the nonmetals, they actually have multiple charges. You guys need to know that for the exam. So when you're naming this, because you know that antimony can form multiple charges, then you need to break it into ions. This is going to be Sb plus 4, F negative 1. Because fluorine has its correct assigned charge, then the name of this is going to be antimony 4 fluoride. So that's how you find SBF4. And remember that there's a space between antimony and the Roman numeral. Going back to our list, we are now going to move on to Lewis structures. Is antimony, tin, lead, and bismuth. When you look at the periodic table, they're actually like in their little corner. So tin is 50, element 50, antimony is 51, lead is 82, bismuth is 83. So those four, they live on group 4A and 5A. So those four in that little corner, element 50, 51, 82, and 83, they have multiple charges. They make ionic compounds. When it comes to Lewis structure, what is the specific question on Lewis structures? How to build them? I need to know a little bit more because the next three topics are all tied together. So what is the question on Lewis structures?
Mainly how to draw them, professor. That's like I was working with one of the classmates. It's the hardest thing to kind of just draw them and get their electronic, like their shape correct. That makes sense.
So let's go through the rules. Let's learn how to draw them, do electron group geometry, because again, the next three topics, Lewis structures, polarity, and attractive forces, they are all together. So I'm just going to check them. And in the meantime, make sure that you gather the list, because after we finish with these, we're moving to chapter 7. Let's just see what questions people have on chapter 7. So let me talk about Lewis structures by drawing Lewis structures. Let's see from here. Okay, let me maybe take these two. Actually, let me take these three. So when it comes to Lewis structures, Okay. Understand that here we're going from name to chemical formula. And when I gave it to you guys in the chapter quiz, in the extra credit, I don't know which one of the two, I gave you guys the chemical formula for it. Okay. So nitrogen triiodide is Ni3. Silicon tetrabromide is SiBr4. Carbon dioxide is CO2. Okay. Now, by now, because we know electronegativity, remember that your central atom is the least electronegative. Okay. So your central atom, for the most part, you can tell because it is going to be the less frequent, the one that has the smallest subscript. But also based on electronegativity, you could tell which one is going to be the central atom. Now, in this case, for example, in Ni3, if you base it on electronegativity, you will get it incorrectly, because then you'll be like, oh, but wait, iodine is less electronegative than nitrogen. So in here, understand that the one that has the smallest subscripts tends to be the central atom. Don't complicate your life. Unless you have 5 atoms that are all different, then you can use the rules of electronegativity. I like to actually use the one that has the highest metallic character, okay? Because electronegativity, sometimes people just look at the numbers and call it a day. In metallic character, since it's a trend, that is a little bit easier. But in nitrogen triiodide, my central atom is going to be nitrogen. And again, I'm building a covalent compound. So I'm placing next to the nitrogen all of my atoms, okay? We need to calculate the valence electrons here. So based on the group number, nitrogen will contribute 5 valence electrons because nitrogen lives in group 5A. Iodine lives in group 7A. So that means that every iodine is going to provide 7 valence electrons. And since we have 3 iodines, okay, then this is 21. We are going to add these 2 values. So there's 26 valence electrons available for bonding. Okay, you're going to start completing the octets from the outside atoms in. Remember that when it comes to the exceptions to the rules, you guys are responsible for knowing that hydrogen only wants 1 line, beryllium wants 2 lines, boron wants 3 lines. The expanded octets that happen to fluorine, to sulfur, to chlorine, what is the central atom? I'm not going to test you on that. If you take upper level general chemistry, then you will see it there. So when it comes to this, we're going to start completing the octets from the outside atoms first, okay? So far, the 3 lines that we actually put around nitrogen, how many electrons do they represent total? Excellent. Each line is 2 electrons, so there's a total of 6. Great job. So I already used 6 electrons in this system. Again, I'm going to use my highlighter tool. So those are my 6 electrons. So I got 20. Let me start completing the octets, again, of the outside atoms first. So iodine already has 2, so it needs 6. It gets 2, 4, 6. So that means that I'm subtracting 6 from 20. The other iodine also needs 6. We have 8 left. One, two, three, 4, 5, 6. Minus 6. We still have 2 electrons. Where do we put those 2 electrons? You know, the iodines are happy. Excellent job on the nitrogen. Okay. Now, does this make more sense? Put a 1 in the chat. I just want to make sure that people understand this process. Now, when it comes to the other stuff, the Vesper rules of it, okay? Let's just start dealing with first, bond polarity. There was a question in the chat earlier when we started the review of like, how do I know the difference between bond polarity and molecular polarity? Because of the terms. If I'm asking about bond polarity, the question is going to say, you know, the type of bond, okay? When we have the type of bond, in this molecule specifically, we are comparing nitrogen to iodine. And when you're looking at bond polarity, again, the question will say bond polarity. You go to, your strategy is to go to the table for electronegativity. You're going to copy the numbers down. So nitrogen is 3.0. Iodine is 2.5. The difference between them is 0.5. Then if you go to the study guide, in the study guide, you know, below the electronegativity values, you have, you know, what makes something non-polar covalent, polar covalent bond, or ionic bond. Thank you, Gia, exactly. When you have a difference of 0.5, this bond is going to be specifically polar covalent bond, okay? Now, let's go through the electron group geometry. That's Vesper rules. When we're doing the Vesper rules, also in the study guide, you can see that there's the table for the Vesper rules. I already put it there. So when you look at the Vesper rules, you need to understand, what are my electron groups, okay? And electron groups can come in different ways. It could be a lone pair, it could be a single bond, it could be a double bond, it could be a triple bond, but they all count as one group, okay? So that nitrogen, so we look at the nitrogen. How many electron groups are on nitrogen? Great, 4 electron groups. So since we have 4 electron groups, and let me show you guys in the slides for chapter 6 where we get this information. So this is the table of electronegativity. It is in the study guide. This is the chart that makes you determine what kind of bond you have is also in the study guide. And then the Vesper rule table is this. It is also in the study guide, okay? So at first, you would determine the electron groups. So now we're looking at things down here, okay? So if we follow the table, the second column is, what is the electron group geometry? Well, electron group geometry, as long as you have 4 electron groups, you're tetrahedral, okay? Our nitrogen triiodide is where we have 3 bonded atoms and 1 lone pair. The angle is 109, okay? So that means that the molecular shape is trigonal pyramidal. So you have to utilize this table to understand electron group geometry, bond angle, molecular shape. Let me write that information here. So electron group geometry, tetrahedral, molecular shape is trigonal, pyramidal, bond angle is 109 degrees. Okay. Yes, the lone pair is the two dots on top of the nitrogen. And another word that we use for lone pair is non-bonding pair. Those are the two words that we utilize. So remember, bonding pairs are going to be the lines that are connecting the atoms. Lone pairs are going to be the dots that are present on each of the atoms. And then they're also called non-bonding pairs. Now, going to overall polarity, okay? In overall polarity, when it comes to your notes, this is the slide that will help you to determine overall polarity. And because our electron group geometry, as you can see here, this is based on electron group geometry, is tetrahedral, then understand that you will look at the conditions that makes a tetrahedral non-polar. And if it's not met, as you can see, the molecule is polar. For a tetrahedral molecule, we need 4 identical, quote unquote, and as you can see, the definition that was said in class by Francisco, really awesome. Remember, identical means that their central atom is attached to a single type of atom via any bond. So we need to have that atom, okay, in the same direction, in all 4 directions. We need to be attached to that atom via any bond. So when we look at the example that we were working with, this is a tetrahedral. Does it have 4 identical, atoms attached in every direction via the same bond? Excellent, it doesn't. So because it does not, then the molecule overall, again, molecular polarity or overall polarity, this molecule is polar, okay? There's a question in the chat about the groups. So electron groups, you just need to know that by definition, and it is also in the slides. Let me just go here so I don't have to flip. Again, electron groups, each of them represents one group, and it could be a lone pair, a single bond, a double bond, or a triple bond. So that's where I got my electron groups. By looking at the molecule of nitrogen, and saying, oh, nitrogen has 1 lone pair, that's 1 electron group. 1 single bond, 1 single bond, 1 single bond, that's 3 additional electron groups. That's where the 4 electron groups come from. So this molecule is polar. So let's go through the last portion of it. So my molecule is polar. When the molecule is polar, okay, then understand that we're going to focus on the strongest attractive force, because in the chapter quiz, I already test you guys on knowing all of the forces. When it comes to the attractive forces, okay, this molecule is polar. So there are 2 things that it can be. It could be dipole-dipole or H bonding, okay? Dipole-dipole is in any polar molecule. Hydrogen bonding, you need to be polar, and you need to have a hydrogen bonded to fluorine, oxygen, or nitrogen. So for this molecule, okay, understand that since there's no hydrogens in it and it's polar, dipole-dipole attractions. Is the strongest attractive force. Questions on Lewis structures, how to determine electron groups, how to determine Vesper rules, meaning electron group geometry, molecular shape, bond angle, polarity of a molecule. For any student that wants to practice more the Lewis structures, you have a lab. So when it comes to this, lab 5 is all about Lewis structures and attractive forces. Practice by, doing the lab. Excellent. Since there are no questions, then let's move on now to the concepts of chapter 7. So in chapter 7 is where we start our chemical quantities and reactions. Any concepts of chapter 7 that we need to clarify? Okay, so here, conversions. Okay. The question in the chat about sig figs, understand that the sig figs are determined by the measurement given. So if the measurement I give you has 3 significant figures, then your answer needs to be rounded to 3 significant figures. Oxidation number. How to find grams within a compound. That's going to be in the conversions, oxidation reduction, and then balancing equations. Okay. Oxidation reduction. So the main thing that I'm going to explain when it comes to conversions is how do I know what the heck I'm supposed to use in order to convert something? Okay. We will talk about oxidation and reduction when we do oxidation numbers and how do I know that it is doing reduction or oxidation depending on gaining electrons and all that kind of stuff. Just really quick, when it comes to oxidation reduction, I always think about it of, okay, if what I'm gaining in my life is something that is negative, right? Let's put it in oxidation reduction. Let's use an analogy. Let's say that you're gaining in your life negativity, okay? Is your happiness going to be increased or reduced? When you're gaining negativity, problems, negative people around you, chisme around you. Exactly, your happiness will be reduced unless you like chisme or anything of that. So when you are gaining negativity, your happiness is reduced. So you're undergoing reduction. And what is oxidation? The opposite. You're losing electrons. So you're becoming a more positive person. Okay. So you're undergoing oxidation. The thing is, like, there's no really good analogy for how oxidation relates to like a sentiment in life. But if anybody come up with the one, let me know. So at least I can explain the reduction. If something is gaining electrons, gaining all that negativity, their happiness will be reduced. The one that is losing electrons becomes more positive, then that one is getting oxidized. That's the best that I can do in terms of analogies.
Can you say that again, Professor? So oxidation, you're gaining negativity?
No, think about it.
No.
Are you going to be having an increasing happiness or reduction of happiness if you have negativity towards you? Like, people are just talking trash, and then problems are coming, and then you get an unexpected bill. Is your happiness going to be increased or reduced when you got problems, negative energy towards you?
So if we're going to try to relate this, oxidation is gaining electrons.
No. Gaining electrons is gaining problems. So your happiness is reduced.
Okay. So oxidation was gaining electrons. Oh, I got it. Hold on, let me write it down.
Yeah, write it down. So when we are gaining electrons, we're gaining negativity, our happiness is reduced. Yes, oil rig is another one, or my son's favorite, because his name is Leonardo. It's like, Leo, the lion goes grr. Oil stands for oxidation is losing electrons. Rig is reduction is gaining electrons. Leo grr is losing electrons, oxidation. And then grr is gaining electrons, reduction. Yeah, oil rig is another way to know oxidation reduction. It's like, if oil rig and Leo grr don't work, then I always go to negativity. When you gain negativity, your happiness is reduced. So that is what gets reduced. Whoever becomes more positive gets oxidized. I need to find out something in terms of oxidation and being happy. I'll figure it out. Yeah, oxidations, you're losing electron. I need to figure
oxycodone, because you have, I don't know.
Actually, right? Like, I can just look at a biochemical molecule. I will look at the biochemical molecules. If I put it on, no, I'm not gonna put it out there because this has been recorded, and all of a sudden it'll be like, oh, Dr. Luz said that oxy makes you happy. No, Dr. Luz didn't say that. Don't do that. Drugs are bad for you. No. This is not going to take me down. All of a sudden, YouTube is contacting me. It's like, Professor, we need to take your lecture down. You're just saying bad things. You never know. People will take that little clip and then all of a sudden say, like, Dr. Luz is encouraging students to use drugs. Please don't. No, let's not.
We'll just use oil and rig. I think.
Yeah, oil rig, Leo grr, we're good. That's it. So going back to the conversions. When it comes to the conversions, understand that there are two sets of calculations that you guys need to know for the exam. So if you look at the study guide, there is a set of calculations, okay, that you need to do by converting between moles and grams, moles and atoms, okay? So when it comes to these conversions, again, item 2 in the study guide, you have moles in the middle. Moles can take you to atoms or molecules. Moles can also take you to grams. That's the basic conversion, okay? Now, when do you know that you're using this specifically? Because we are comparing, okay, at first, in terms of the calculations, moles of an element to atoms of an element. So when it comes to an element, okay, you are given moles, and then maybe you're looking into atoms of an element. And understand that when that is the transition, Avogadro's number is your conversion factor. Okay, always. Doesn't matter if you're going from moles to atoms or molecules, or atoms and molecules to moles, okay? Now, if you're going in this direction, meaning you were given moles and you have to find atoms, okay, we're going to multiply by Avogadro's number. If we're going, okay, from atoms or molecules back to moles, we are dividing by Avogadro's number. So this is the chart that I gave you guys. Okay, so we're talking only about this corner, going to moles to atoms, atoms to moles, moles to molecules, or molecules to moles. Okay, that's the conversion. How do you know that this Avogadro's number is the only thing needed? Look at the questions, you guys. How many molecules do I have in these moles? How many atoms do I have in these moles? How many molecules do I have in these moles? Look at the conversions. All we're doing is using Avogadro's number. So when you're given moles and you're trying to find atoms, we're going to multiply by Avogadro's number. Like in number 4, you are giving atoms and you want moles, we're going to divide by Avogadro's number. And then notice that in the question, you have, hey, moles of carbon, atoms of carbon, or it could be moles of a compound, atoms of a compound, okay? As you can see, like in number 5, you're trying to find moles of a compound, but you were given atoms, or you were given molecules, sorry, of that compound. What we're gonna do, divide by Avogadro's number, okay? Does the conversion between moles, atoms, or molecules make sense? Let's put 1 in the chat. Okay, so remember, what makes the difference, so don't be confused so much about the term atoms or molecules. For those of you that are like, how do I know? When you are producing atoms or given atoms, we're talking about an element. When you deal with molecules, we're talking about compounds or diatomic molecules. The question in the chat says, so the arrows for formula subscript just mean both are using formula subscripts. So formula subscripts, we're not there. So remember that when it comes to formula subscripts, we have already done moles of compound to moles of element. That one we did. But yes, what the flowchart is saying is like your conversion factor is the formula subscript. That's it. So that's the first type of calculation, okay? Using Avogadro's number. Second type of calculation, going back to the notes, is if I'm dealing with, again, the left side of the slide. The conversion factor for the formula subscript is the formula subscript, but we will deal with them in a moment, okay? So when we have moles of element, let me see, or compound, let me just finish this. So again, the right side, we're good. The left side, moles to grams, okay? My conversion for that is the molar mass. Okay? It doesn't matter if I start with moles of an element, moles of compound, moles of a diatomic molecule, okay? My transition between grams of something to moles of something, regardless of what it is the molar mass of that. So if I'm given grams of an element and I need to transition to moles of that same element, molar mass is the way that I get there. If I'm giving grams of a compound and I need to find moles of that compound, then again, I use the molar mass of the compound or the diatomic. So when it comes to the wording, look at how the problems look like. How much do 8.13 of this element weigh in grams? If you're given this many moles, how many grams would you have? That's how you know, oh, click in my head, I just need the molar mass of whatever single element or single compound I'm dealing with, okay? Questions on transitions of moles to grams. This is how it looks like. There's another conversion, since there are no questions. The next conversion that you guys need to know for the exam I'll show it right now. So if you are given moles and you need to find grams, you're going to multiply by the molar mass. If you're given grams and you need to find moles, you need to divide by the molar mass. So if we look at the sample problems in the in-class worksheet, look, we're given moles, we're finding grams, we're multiplying by the molar mass. Like in number 4, we're giving grams, we're trying to find moles, we're going to divide by the molar mass. Put a 1 in the chat if this is helping you. Because I just want to know that breaking it down like this, remember, when you're encountering these questions, all you guys have to do is literally read the question. Read the question. Let me go. Let me show you guys examples just in case. Let me preview it. Stop sharing. Let me reshare this. Okay. So this is chapter 7 quiz, right? Okay. This is the for those of you that have to still do it, right? Look at the first question. How many carbon atoms are in 3.85 moles of carbon. So what is going to be our conversion factor? We are given moles. We need to find atoms. Avogadro's number, excellent. Now I was given moles. Remember the notes that I just gave you. Since I'm given moles, am I going to multiply by Avogadro's number or divide? Great, multiply. See, you guys, this is what I tell students, and then, you know, some students think I'm very silly when I say this. Think, unless you're afraid of dogs, think of the exam like a puppy. Like, for the most part, you guys, puppies are not intimidating, right? So be like, oh, this exam is just like a puppy. So these questions, don't look at them and be like, oh my God, I don't know how to handle them. Picture them like a puppy. I can read the question. I know what the question is asking me. There will be some questions that are like, she's making me think a little bit longer, but it's okay. This is a puppy, okay? Again, unless you're afraid of dogs. If you're a cat person, think that it is a kitten. Let's go to question number 2. How many molecules are present in 4.25 moles of carbon tetrachloride? We're finding molecules. We're going from mole to molecules. What do we need? Great, we multiply again by what? Great job, avocado. See, you guys got this. Oh, not avocado. Avogadro. Avogadro's number. Look at this one. I gave you molecules of ammonia, but we want moles. What are we going to do? Division. Great. We're going to divide by Avogadro's number. Classification. No. Let me see. Moles. We will deal with this in a moment. Moles. This is molar mass. This is another one of finding atoms. Oh, look at this one. In question 11, okay? How many grams of this compound are in this many moles of this compound? Okay, so our transition is, oh, she gave me moles. I'm trying to find grams. Okay, great job. We multiply by molar mass. How are we feeling, you guys? We're feeling better, right? Like, look at the question. The question is telling you, oh, this is what is given and this is where I'm going. Let me see, is there another one here? Make sure that you practice, but at least the important thing when it comes to this, you guys, is that you are able to understand the question. Like, what is the question really asking? Let's go back to the notes. So now that we know, okay, if I'm given moles and I'm dealing with just with element to element and then compound to compound, I can identify that. Now, there is another type of question. Let me just show my notes.
Professor, just a question. So for Avogadro's number, we're only using that number when we're going from moles to grams.
No, when you're going from moles to atoms, or atoms to moles, or you're going from moles to molecules, or molecules to moles.
So
if you look at the chart, okay, see the transition, moles to atoms. That's where Avogadro's number is sitting.
yes.
So only for those transitions is when you need it.
So only from moles to atoms do we use Avogadro's number.
Or moles to molecules, and vice versa. That's why I have a double-headed arrow.
Got it. Okay, I just wanted to make sure those. I think, like I said, that was probably the trickiest because, like, Avogadro's number, we know that we use it for moles to atoms, but it was the molecules. Like we use it for molecules as well.
Yes, it's just that remember that Avogadro's number is something that we use in chemistry to count things. So you know that, for example, like if you go and get like a dozen, of oranges, you get 12 objects. In chemistry, we count atoms and molecules by counting using Avogadro's number, 6.022 times 10 to the 23rd. That's how we count in chemistry when we count atoms or molecules. Now, when it comes to the other conversion that you guys need to know, okay, is if I'm given the amount of moles or grams of a compound, how do I know how many grams of an element do I have? Okay. So that is the one that is a little bit more complex, right? Because you can start, and let me just guide you from the answer, the in-class worksheet. So we already did this one, okay? It is these kind of problems. The professor gave me grams of compound. So this is where you start. This is where you end. When the problem guides you through this, or is asking you to do this, then you know that you need 3 pieces of the puzzle. You need the molar mass of your compound, you need the formula subscript, and lastly, you need the molar mass of the element that you're interested in. And when you read the problems, the problem is going to guide you through that. You're going to get grams of the compound, or you're going to get, and then you're going to be asked to get grams of an element. That's how you know that these 3 steps. So this is what I was talking to you guys yesterday in class about strategy. Okay, you need to read the question and say, okay, the question is telling me to do these steps. Let me see from, let me show you an example from the chapter 7. This is from your chapter 7. See how it says 42.7 grams of ammonium nitrate contains grams of nitrogen. That's how you know that you will be going to that flow chart that I just showed you. I will write it in a straight line for those students that benefit from seeing it differently. Let me just.
This one, do we have to write the chemical formula?
For that one you do. And again, for this, the reason, because this is another way to test you guys on naming. So that's why it is there, okay? So I'm just going to rewrite this in the notes that we have for today's review. So if we have as a conversion grams of a compound, and you need to convert it to grams of an element in a compound, you need 3 conversions. Always, always. The first thing, at least in problem 12 in the chapter 7 chapter quiz, is that you need to know what is the chemical formula for ammonium nitrate. But earlier today, we went over that, okay? Now, when we are given grams of a compound, We need 3 conversion factors. Always the same 3. Okay? The first conversion factor, you're going to put on top 1 mole. Okay? And then you're going to put the chemical formula of your compound. So 1 mole of your compound. And in the bottom, you're going to put grams of compound. Where do you get these numbers? From the molar mass of your compound. In the next conversion factor, we're going to put X moles, well, actually, 1 mole of compound, because it's going to be always 1 mole of compound. And on top is going to be X mole of element. Why do I do X number of element or X moles of element? Because this X that you guys see here is based on the formula subscript. The last portion of this is going to be, in the bottom, you say 1 mole of your element. And on top, you're going to write grams of an element. Where do you get that? Periodic table. That's where you get the number for the gram. So wherever you see the X, is that because you need to find that information somewhere. So this X comes from the molar mass of the compound. This X comes from the formula subscript. This X comes from the periodic table. Let's practice at least one problem, because this one is the one that gives students a little bit of a headache. Oh no, that's in chemical reactions. Let me see. Let me take this one and change the units. Okay. So let's try the following problem. We needed to find grams of nitrogen in this many grams of vanadium 5 cyanide. Again, this is a review. Vanadium 5 cyanide. Let's write the chemical formula in the chat. vanadium 5 cyanide. Great job, Elle. Thank you. This is VCN5. Okay. So if I have my compound in words, I need to write the chemical formula. Again, in this compound, we have vanadium, we have carbon, we have nitrogen. We're only interested in the nitrogen. Again, utilizing the flow of work that I just wrote there, you're going to write what it was given to you. 5.25 grams of VCN parentheses 5. In a problem like this, we have 3 conversion factors. Always, you guys, always. So in the first one, as you can see on top, I'm going to write 1 mole of VCN5. On the bottom, grams of VCN5. You need to calculate the molar mass of this. So you go to your periodic table. Let me find mine. I have it here. I'm going to do carbon. I have 5 of them. So the molar mass of this, you could do it along. We have vanadium. We have carbon, which we have 5 of them. Nitrogen, we have 5 of them. Okay. Do people see and understand why is it that we have 5 carbons and 5 nitrogens? Great. So I'm gonna do vanadium first. Vanadium, that's in group 5B. We have 50.9415, and I'm going to add to that the result of taking carbon, which is 12.0107 times 5. Oh, you didn't do it times 5. 12.01. Sorry, I have to say my numbers in Spanish. Because if I said them in English, for some reason, it doesn't make sense. 12.01, 0.7 por 5, más 50.94, 1.5, más 14.0067 por 5. I got that, yeah, 181.0285. That's what I got. $181.0285. That's where we got that number. Okay. Look at the next, where we have the pink area. I'm going to write in the bottom 1 mole of VCN, and then 5 in the bottom. Okay, 1 mole of compound. On the top, I'm going to write mole of nitrogen, because that is the element that I'm interested in. Based on the formula subscripts, how many nitrogens do we have? Let's put it in the chat. Great job. So I put a 5 here. And then my last portion, as you can see, is saying 1 mole of nitrogen. And then I'm going to write specifically the molar mass of nitrogen, which is 14.0067 grams. Okay. Put a 1 in the chat if what we did up there and what we wrote down for this problem makes sense. I want to make sure that people understand it. And again, if your transition is from grams of compound to grams of element, this is always the process. Always, always, always. Now, to finalize this, I'm going to do 5.25 times 1 times 5 times 14.0067 And that number I'm going to divide by 181.0285. I have a calculator display of 2.0310, yada, yada, yada. Great job. But then based on the digits that I was given, I need to round to 3 sig figs. So this is 2.03 grams. So this is mainly those calculations that we were mentioning. So let me go back and share from the chapter quiz. So that process is what you use for question 12. See on question 11, that is telling you, oh, we start from moles. Remember that here you're going from moles to grams. This is what we, not this process. This is a different, this is, oh, I was given moles of compound, grams of compound. This is just the molar mass of the compound. So for question 12, the process that we just did is where it applies. Question 13 is like question 11. Question 14 is like question 11. We're just transitioning between moles and grams of the compound. This is just a reaction in words. Yeah, this is just coefficients. I think this question 19 in the chapter quiz, which we also have an example in the extra credit. This question, you guys, make sure that you practice. There is a question similar to this that you need to encounter. I already tested you in the chapter quiz, in the extra credit. Again, you're given something, you need to balance the equation, then you do the math. But then this is for chemical reactions. So this is different. Yeah, no problem. So any questions about the transitions that we did? Just, again, moles to atoms or molecules, moles to grams, grams of compound. Give me a moment. Let me just open it on my side. Preview. So on question 7 in the extra credit, that is a mole to mole transition, and that is that one I haven't mentioned yet, but that is just using the formula subscripts. So for if you're giving moles of something and you need just the moles of the atom, if we go back to the flow chart, so for question 7 is more on, let's see, is it here? It's just basically this portion. You're given moles of compound, you're going to moles of element. Exactly, you need to know the chemical formula for it. And that is in the, whatchamacallit, in the common name table thingy. That's where we got that information from. So again, when it comes to these questions, you guys, it's not that as long as, this is what, again, like I mentioned earlier today, strategy. You read the question, you know where you need to go and how to use it. So if you're giving moles of the compound and the question is asking you for moles of the element, the formula subscript is the relationship. Let me just give it to you guys in terms of the notes for today in straight chain, I guess, sideways. So if you go from moles of compound to moles of element, then you use the formula subscript. And then basically that is more along the lines, like if the problem says, let's say that you have 3.80 moles of let's say water. And then you need to find specifically the moles of H. Then you will say, oh, 3.80 moles of H2O. I only have one conversion factor, and that is the formula subscript. In the bottom, you will say 1 mole of H2O. And on top, you will say, oh, 2 moles of H. Exactly, great job. So we're going to multiply those two, 3.80 times 2. And then you will say, oh, okay, this is 7.60 moles of H. So that's how you do that one. So make sure that when you read the question, you know, make sense what the question is asking of you. Let me go back to what else of chapter. Oxidation reduction and balancing equations. When it comes to balancing equations, you guys, the main thing that you have to remember is that you want the same number of atoms on either side. So you have to be conscious. We can practice. I have some problems in balancing equations. Let's do balancing equations before oxidation numbers. The main thing, yeah, it is true. Balancing equation is trial and error. And then the more that you do it, the better you get at it. The only one, oh, let me bring one that has polyatomics, because I think that is one of the ones that sometimes give student headaches. No, I want a polyatomic that everything is together. Let me do this one. Okay. So the same atoms that we have on the reactants, they need to be in the products. If we look at problem B, we need to write in what we have, which is silver, iodine, sodium, and sulfur. On the other side, you need the same thing. Because remember that in these reactions, there's no elements that appear out of nothing, okay? So let's count what we have of each. We have 1 silver, 1 iodine, 2 sodiums, 1 sulfur. We have 2 silvers, 1 iodine, 1 sodium, 1 sulfur. So at first glance, we can say, oh, the iodines look balanced, the sulfurs look balanced. Like at first. But then understand that if you are trying to then balance the silvers, that's going to affect your iodine, right? So we have to start somewhere. So let's say that we start with the silver and I put a 2 here. That takes my silvers to 2. That takes my iodines to 2. Okay. Now, when I look at sodium and iodine, ooh, they are in the same compound in the product. So if I put a 2 here, that takes the sodiums to 2, that takes the iodines to 2. We have the same number of atoms on either side. I didn't put anything in front of the sodium sulfide or the silver sulfide, so they get a value of 1. I think that's another common mistake that I see in exams. That student says like, oh, but I didn't put anything, so that's a coefficient of 0. We have never said that when we are reading these, we're gonna say, oh, 2 moles of silver iodide react with 0 moles of sodium sulfide. That makes no sense. It has to be 1. So if you don't put a coefficient, put a number of 1. Okay. Let me go through I, which is the one that sometimes, students break it into all the elements, but you don't need to, especially if it's a double replacement reaction like this one. So when I am taking into account what I have in my reactions, I'm going to write iron, bromine, but look that in the reactant and in the product, SO4 is a unit. Treat it as a unit. Hydrogen is by itself and SO4 is a unit. Don't, especially in double replacement reactions. If SO4 or any polyatomic ion, especially in double replacement reaction, because they're going to be as a unit in the reactant and the product, treat them as a unit when you are balancing the equation. So here we're going to say FeBrH and SO4. That's what we have. Let me take into account how many I have of each. 1, I have 3 of these. I have 2 of these. I have 1 of these. Iron in the product, I have 2. Bromine, I have 1. Hydrogen, I have 1. The sulfate, I have 3. Okay. So as you can see here, nothing is balanced. We need to start somewhere. For me, the easier route is to start with the polyatomics. So I'm like, you know what? There's 3 sulfates on the product. Let me just put a number 3 here. And say, oh, now I have 3 sulfates. But this also affected my hydrogens. Now my hydrogens go to 6. Put a 1 in the chat if so far is making sense. Now, when I go to the products, now I have to make sure that my hydrogens, I'll wait. Yes, because this is a double replacement reaction. In double replacement reactions, the easier way to do this is because SO4 shows up together in the reactants and it shows up together in the product, then I keep it together. It's only for double replacement reactions. It's the way to go. So now, once I have this, then I'll tell myself, okay, then you know what? I'm going to target that hydrogen. I need 6 of them. But putting a coefficient of 6 in this bromic acid, then that means that bromine goes to 6, hydrogen goes to 6. Now, the last thing that I need to make sure is that I match my bromines in the iron. Oh, look, they're together. So if I put a 2 here, my iron goes to 2, balance, my bromine goes to 6. So again, in double replacement reactions, keep the polyatomic together. Excellent, yes. So the iron 3 sulfate, that will be a 1. So if you did not put a coefficient, put a 1 on it. So make sure that you practice. The more that you practice, the easier they go. I don't know. It just takes practice. Let me see. We have only done 2 chapters.
Professor, you said double replacement. What was the for double replacement?
Yeah, for double replacement, keep the polyatomics together. Let me show you guys an example of when not to keep them together. Chapter. See, like, look at this problem. Look at H. See how phosphate is together? And then you see it as PO4. So when you have things like this, then, you know, I will say, oh, I have calcium, I have chlorine, I have sodium, and I have PO4. Those are my components. Again, because this is a double replacement reaction. We did that one. See, like in this one, I'll say I have NH4, PO4, PB, and NO3. Because it's a double replacement reaction. Let me see if I have one that. See, look at letter D. You cannot do that on letter D because look, in the products you have OH, but then on the reactants you have it in H2O. And then also hydrogen is divided between the 2 products. So in this problem, I wouldn't treat it as OH because I don't see OH on both sides. Let's go over oxidation reduction. Yeah. So oxidation numbers was the last topic in chapter 7 that students wanted to go over. So there are some general rules when it comes to oxidation numbers, okay? And remember that the rules are in the slides. Let me guide you to where you find those notes. So this is slide 17. So this is where you find the calculation of oxidation number. So when it comes to this, we need to know that any element that it is in ground state or elemental form will have an oxidation number of 0. So if you see the symbol of the element by itself, you guys, then you know that that's going to have an oxidation number of 0. So in problem B, who gets an oxidation number of 0? Just put it in the chat. Again, if you see an element by itself, just the symbol. Excellent. Calcium has an oxidation number of 0. What about in letter C? Who gets an oxidation number of 0? And Yesenia, you are correct. The people that put oxygen, I'm going to deal with oxygen in a few moments. Yes, zinc get a 0. Who else gets a 0 on letter C? Silver gets a 0. And great point you guys made. You are paying attention. I'm so proud of you. When it comes to the letter B, diatomic molecules also get an oxidation number of 0. Also. So other than having elements, diatomic molecules, also oxidation number of 0. Okay? Do not confuse diatomic molecules, or if you see something that looks diatomic and is not. This is a common mistake that I see sometimes that students make. They're like, but Dr. Luz, you said that O2 has an oxidation number of 0. This says CO2, give credit to carbon. Carbon is sitting next to oxygen. I didn't say that O2 has it. I said that molecular oxygen has. This is not molecular oxygen. This is carbon dioxide. So this O2 doesn't have an oxidation number of 0. The one that we have in letter B does, because that's molecular oxygen. CO2 is a molecular, in other words, a covalent compound. So don't be thinking of like, oh, if I see an O2 or I see an H2, I see an N2, that's no. Remember, the diatomics. You can memorize them by knowing this made up word, which is called Brinkelhoff. That's a made up word, Brinkelhof. It sounds German, right? Anyways, Brinkelhof is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those are your diatomics. The elements given by the word Brinkelhof. Continuing on. Now, we see, for example, in letter B, that we have the atom of oxygen. Oxygen always has an oxidation number of -2 unless it is in peroxide. That's it. So we know that my oxygen has a charge of -2. Or let me write it here. And I know that my calcium has a charge of +2. And in general, when you have ionic compounds, you guys, the charge of the ion is their oxidation number. So calcium is +2, oxygen is -2. So when we think about it in terms of what happened, here we have calcium and oxygen. Calcium went from 0 to +2. Oxygen went from 0 to -2. Whoever became negative undergoes reduction. But like we agreed earlier today, we're only using oil rig. Oil rig is oxidation is losing electrons. Rig is reduction is gaining electrons. Okay. So who got reduced? Who got reduced? Excellent. That means that the other one got oxidized. And we don't have an spectator ion in this one. Let's move on to letter C. In letter C, our first compound is an ionic compound. So I know that the oxidation number for silver is going to be +1. Now, NO3 has an overall charge of -1. So we have to do a little bit more work to find out what happened to nitrogen and what happened to oxygen in this system. Whenever you have a covalent compound, understand that you need to give the second nonmetal its oxidation number. For oxygen is -2. You need to multiply it times the subscript. So what is the overall oxidation number of oxygen in NO3 minus? Great, -6. We only have one nitrogen, but when we add the oxidation number of nitrogen to -6, it needs to equal -1. So what is the oxidation number of nitrogen? Remember, it's oxidation number. So we only have one nitrogen. Remember, it has to equal -1 because nitrate overall is -1. Remember that for your polyatomics, this rule is the one that is a little bit more complex here. I'm just teaching it to you guys just to remind you of it. If I have NO3 -1, the addition of these two oxidation numbers, oxidation number for nitrogen, plus the total oxidation number for oxygen needs to equal -1. So if in the context of NO3, the sum of my oxidation numbers needs to equal -1, and I know that the second one is -2 times 3, that's -6. Nitrogen, we only have one of them. Excellent. The oxidation number of nitrogen is 5. Oxidation number of nitrogen is 5, plus the total of 6 that oxygen is contributing in the context of this. That's what equals your -1. I just want to remind you of it. Because in this, the nitrate is not doing anything, but I just wanted to show you how to calculate it. So we know that nitrogen is +5. Oxygen overall is -6, but by itself is -2. Okay. Remember, the -6 comes from the multiplication of the -2 times 3. If we look at the product, zinc is in an ionic compound, so it's +2. And look, NO3 is still -1. So in a way, I just show you guys how to calculate it for NO3, but in the context of this compound, we have NO3 on both sides. So let me make some notes here. This is still NO3 -1, where the oxidation number of nitrogen is +5, oxygen is -2. In this context, nitrogen is still +5, oxygen is still -2. So the only changes here happen at silver and at zinc. Okay, who got reduced? Excellent, the silver. How do you know that the zinc is what got oxidized? Look, it has a positive number. It got oxidized. Exactly. No. Remember that you're not gaining positivity. You're losing electrons, and that's why you're becoming more positive. So who gained the electrons here was silver. Look, silver was positive and it went towards 0. So that means it got reduced.
So for oxidation, when it comes to polyatomic ions, we have to get our oxidation numbers from the polyatomic ions, like NO3.
It depends. Like in this reaction, I wouldn't even bother because the NO3 shows up the same way on either side, on both sides. So immediately in my brain, it clicks, oh, if NO3 shows up in the reactant and in the products, that means that that is going to be my spectator ion. Exactly, great job.
Got it, okay, okay.
But if it's not, let's say that in the product, it would have been like CnNO2 plus AgO, you know, all of a sudden it doesn't have the same identity, then you have to go through the long process.
So that will save us work if we know that because if when I look at it, NO3, it changed because now NO3 on the reactant side is now on the product side NO3 with a chart with the subscript of 2. That's changed, no?
Well, in a way, yes and no, right? Like NO3 as an entity, it hasn't changed because you're still dealing with nitrate. It's just that the reason why the nitrate in the product has that subscript of 2 is because now it's in partnership with zinc.
Got it.
Again, these also take practice. So from chapter 7, I think there was a question that I didn't address yet, which is that the problem, there is a problem like that in the extra credit. There's also one in the chapter quiz of like, okay, let me show it to you guys. Let me see if I can pull it up. Okay, like question 10 in the chapter quiz.
In chapter 10?
In chapter 7. Question 10 in chapter 7. Let me share my screen. And you guys also have a question like that in the extra credit, and you need to know how to do these problems in the exam, which is, Dr. Luz gave me a chemical reaction. I need to balance that chemical reaction, and then I need to do math on that chemical reaction. Okay, so that's the only thing that we didn't talk about in terms of conversions. But these, whenever you encounter this problem, you guys, your strategy is a different flow chart. Okay, let me show you the flow chart that you use for this. In the slides.
Professor, you said this is, oh, this is the extra credit. Sorry, you're looking at that.
This is, yeah, the test 2 extra credit. But this is question 10 in the extra credit. In the chapter quizzes, oh no, let me go to assignments. In this, in chapter 7, chapter quiz, it's it's question 19. You need to write the coefficients of the balanced chemical equations, and then you have to do math based on your balanced chemical equation. Because, you know, after we talked about conversions a few moments ago, then students want to still use it. You could still use that flow chart if you know where you're going. But my recommendation is for this problem, like question 19, like question 10 in the extra credit, your strategy has to be this flow chart. Because this one is for chemical reactions. Okay. Who it is? Oh, give me one moment. That's my mother. Sorry, you guys. I needed to pick up that. Just checking on my mama. So when we have calculations and we are given a chemical reaction, this is the flow chart that we use. There's going to be 3 different calculations that you guys need to be familiar with. Let me just erase all of these. Okay. Calculation number 1. When we are given the mole of something in my chemical reaction, and I need to find moles of another substance in my chemical reaction. Okay. How do I solve that? I'm going to use the mole to mole factor. What is the mole to mole factor? The mole to mole factor tells me what is the relationship between 2 different substances by looking at the coefficients in my balanced chemical equation. Okay, so if I go to the problems that we were doing when it comes to balancing equations, right? And if I ask you guys, how many moles of silver iodide are needed when 4.2 moles of sodium sulfide react? Okay, that's the question. So your connection has to be is like, oh, we are dealing with a chemical reaction. So what I need to do is say 4.2 moles, okay, of that Na2S. I look at my balanced chemical equation. For every mole of Na2S, and sorry that let me do a better job at writing. So if based on my balanced chemical equation, I find 1 mole of Na2S, and on top, I put the coefficient of AgI, 2 moles of AgI. I multiply 4.2 times 2, and that's my answer. Okay. Questions about that first calculation? I am given moles of something. It could be a reactant. It could be a product. I'm just comparing 2 different things in my chemical reaction. That's all I'm doing. Any questions? Let's go through the other type of question that you can encounter. Oh, it's hard to see the yellow. The second one is you are given moles of something and you need to find grams of something else. Let's put in the chat. How many conversion factors do I need for this second question? How many? Great, 2 of them. The first one is my mole to mole factor. The second one is the molar mass of that substance that I'm interested in. Okay. Questions so far? And then the third one is when I start all the way at grams. So I start here and I need to find grams. Again, it will be It could be grams of reactants to a gram of a product, or gram of a product to gram of a reactant. The important thing is that I'm comparing two things in a chemical reaction. So I need how many conversion factors? If I'm comparing two substances in terms of grams, how many conversion factors? Excellent, 3. Let's do at least one practice problem. And I know it's not going to be noon soon. And maybe people want to take a break. I sure have to get something to eat. I feel that I burn so much energy. Actually, let me copy this. Copy. Paste. Okay, so to make you guys' life easier, I'm just going to write the balanced chemical equation. I have magnesium oxide, MgO. Oh. So sodium, solid, magnesium, also solid, produces Na2O, that's also a solid, plus magnesium. Okay, so to balance this equation, there's a 2 here, there's a 1 here, there's a 1 here, there's a 1 there. Questions so far? This in part B is just asking about oxidation reduction. Do we need to go through letter B? Because I'd rather go through the calculations. I can just write the answers. No? Okay. So for letter C, see how it's saying grams of magnesium oxide. So that's what it's given. Let me just make this a little bit smaller. 2.85 grams of MgO. And I need grams of Na2O. Okay? So if I go back to the flow chart that I need for chemical reactions, which is this one, I'm giving grams of one substance and I want grams of another substance. How many conversion factors do I need? Let's put it in the chat. Love to see those 3s. Okay? I need molar mass, multimole factor, molar mass. So let me just write it in the problem that we're dealing with. So I'm going to write 2.85 grams MgO. So what molar mass do I need? The one for magnesium oxide, okay? So on the top, I'm going to say 1 mole of MgO. In the bottom, I'm going to do 15.9994 plus magnesium is 24.3050. This is 40.3044 grams of MgO. Second one, mole to mole factor. What goes on top? Okay, the moles of B, because I need to cancel the moles of MgO diagonally. So in the bottom, I'm going to say mole of MgO On top, mole of Na2O. Okay? So remember, this middle conversion comes from the coefficient in the balanced chemical equation. So what number goes on top, you guys? What is the coefficient in front of Na2O? Great, there's a 1 here. What is the number in front of MgO? Great, that's where we get those numbers. Good so far? Let's put a G for good. G for B can be for gangster too, but that's okay. We're gangster when it comes to chemistry. Oh, I'm gonna start doing that in class. Oh, it can be grams. No, but grams is just, no, we're G, we're capital G's, come on. Yeah, I will be the OG in the class. You guys are the newbie G's. Does that make sense? Anyways, let's continue with this. The last part is molar mass of I only listen to gangster rap when I'm making exams. It gets me in the mood. I'm just kidding, I'm kidding, I'm kidding. Don't. So the last portion here is going to be the molar mass of that second compound that I'm interested in. So I'm going to do in the bottom 1 mole of Na2O, and on top, the molar mass of it. So it's going to be 22.989769 times 2 plus 1 oxygen, 15.9994. So then you get 61.978938 grams of Na2O. Grams of magnesium oxide, cancel with grams of magnesium oxide. Moles of magnesium oxide with moles of magnesium oxide, moles of sodium oxide with sodium oxide. So your final answer is going to be in grams of sodium oxide, which when we do this, we will do that times 2.85 divided by 40.3044. 4.38 grams. Did I do it wrong? That's what I got. 2.85 times 61.97893938.
That was my mistake, Professor. I multiplied times 2. I wrote it down wrong. That was me.
Oh, okay. 40 point. But I'll double check. Again, I'm not perfect. I'm only human. So yeah, I got that, the 4.38 grams. And then, yeah, that one, the particles of magnesium, that's not relevant to you guys. But I hope that now when you encounter that question in the exam, you know what flow chart to go to and how to follow the process, okay? So far we have reviewed chapter 6 and 7. I think we should take a break.